So now we will, for the rest of the class, we'll talk about the last topic, which is public goods and externalities. So we're going to start with externalities, and then we'll talk about public goods, which I basically think of as large-scale externalities. So it makes sense to talk about externalities first. So some of this stuff should be familiar to all of you from like an Econ 1 class, so we'll go quickly through it, and then we'll talk about what some of the current research is on these topics. So I'll talk, define what externalities are, the most basic model, how do we correct externalities. We will see that we can basically use price methods or quantity methods. And then one of the very interesting papers in this area is by our colleague Marty Weitzman on how you choose between price methods and quantity methods. Then we will combine the externalities part of the class with the optimal tax part of the class and think about second best taxation, like the Ramsey problem when you have externalities. That's what the Sandmo paper does. And then we'll talk about empirical evidence. So what is an externality? An externality arises whenever the utility or production possibility of an agent depends directly on the actions of another agent, right? So it's like if my consumption enters your utility function, then there's an externality. There's a critical distinction between pecuniary and non-pecuniary externalities. So you might think, well, if I buy more apples, that might reduce your utility because while buying apples, I drive up the market price when the demand curve shifts outward, which is going to make you less off because you have to pay more for apples. That is not what we're talking about here, right? That is part of the market mechanism that's priced, and there is no rationale for government intervention through that type of external effect. What we're talking about is something like, listening to loud music where it directly impacts the other person. So the first thing I think that's important to keep in mind is that it's not like there's some deep technological distinction between things that are pecuniary externalities and non-pecuniary. So pecuniary basically means it's regulated through the market, like it's priced. And so we don't care about the pecuniary ones. What this part of the class is about is the non-pecuniary ones. And it's not that there's something fundamentally different about eating an apple and listening to music. What it really is about, and this is where I think Ronald Coase had like a profound impact on economics, it really is about what markets exist. So you can convert all externalities into pecuniary externalities if you had the appropriate markets and appropriate property rights. There's nothing special about pollution or about music or noise or whatever that's fundamentally different. It's that typically we don't have the markets to price those things. And so the Coasian view is the way you should think about externalities is not necessarily thinking about government solutions, it's about completing markets. This is really about incomplete markets. That's the point. Okay, so, and we'll see where that runs into some limits. So here are the main questions. So at a theoretical level, the questions are, naturally in the optimal policy context, what's the best way to correct externalities and move us closer to the social optimum? And then the empirical question is how do you measure the size of the externality? So we'll see naturally that the size of the corrective tax you want to levy depends upon the marginal cost of the externality. How do you measure the size of externalities at the margin? And here you'll see the empirical work is going to be a little bit different in style than all the other empirical work we've talked about in this class. And there's a deep reason for that, which is a lot of the empirical work that we've talked about in this class is basically about recovering demand curves, recovering utility functions, recovering people's own preferences from their behavior. So basically using the tools of revealed preference. But the whole idea of externalities is that you cannot do that, right? It's something that is not captured in that person's own profit function or utility function. And so you can see why you fundamentally will need to use different types of methods. All right, so very simple model that goes back to what we were talking about in the first couple of lectures in the class. So let's say you've got firms producing cars, X cars, using C of X units of the numeraire good Y. So it's this two-good model that we've worked with a few times. But now we're going to add this feature that when you produce a car, you generate X units of pollution. So more generally, there might be some pollution function P of X. And just for simplicity, I'm going to assume P of X equals X here. Consumers, let's assume, have the usual quasi-linear utility function, but now we're going to add this term which reflects the cost of the pollution. They have a minus dp of x. Depending upon the total number of cars produced, the air deteriorates or something, and that has some utility cost for everyone. So social welfare now is total surplus from the production of cars and consumption of the other good minus the damage created by the externality. Okay? And let's let P denote the market clearing price of cars. So let's first characterize what happens in equilibrium. So this is the standard thing. Firms maximize profits, consumers maximize utility. What's important here is consumers maximize utility, taking the level of pollution as fixed. So they do not internalize the fact, even though we've just written this down with one consumer here, you don't take account of the fact that when you consume more X, this P of X term is going up. And that's the usual thing we assume in these tax models. It's just a way to approximate the fact that if I buy one more car, it's basically irrelevant for the amount of pollution. So, on average, I just take the amount of pollution as fixed when I make a decision. So it's an approximation to a model where there's a large number of agents. So my demand satisfies the usual first order condition. The supplier's supplier's profit maximization problem generates the usual first order condition. And so in equilibrium, you're going to get to this point where the marginal utility of consumption of one more car equals the marginal cost of production. But that is not Pareto efficient. Okay, so this usual optimality condition, as you're all familiar with, is not Pareto efficient because you're consuming too many cars. So you might also be producing inefficiently, which I will come to in a little bit. But in this simple model, the equilibrium, the market equilibrium, is that you get to this point where the supply and demand curves intersect, or where private marginal benefits equal private marginal costs. But in fact, the marginal cost of producing the cars is higher by this D amount, the amount of pollution that's generated. And so the social optimum would be here, but the private optimum is overconsumption, so you have deadweight loss given by the size of that triangle, right? Because all these guys who are buying these cars, they value them at less than the true marginal cost of production. And so we basically want to take those guys out of the market. Everybody would be better off if we could devise a system of transfers and get rid of that deadweight loss triangle. So you can see immediately from that you can increase social welfare at a first order level by reducing production by delta X. So we see that with a simple perturbation argument. Suppose I change the quantity by some amount delta X. What does that do to the system? The consumer gains a marginal utility of U prime of X. The producer pays a cost of C prime of X times delta X. And then we have this added term coming from the fact that there's that pollution effect of D. And what that means is, remember, at the optimum, at the market equilibrium, not the social optimum, we have these two terms equal to each other, right? Market equilibrium is going to take you to the point where private willingness to pay equals private marginal cost of production. And so as a result, dW at the market equilibrium is going to be minus D delta X, which means if I have delta X less than 0, I one-for-one get these benefits in terms of the amount of pollution, right? So you can see that in order to calculate dW, I basically need to know what D is. And that's what the empirical research agenda is. What is the size of that externality? All right, so because of this, the first welfare theorem doesn't hold. The market is no longer delivering an outcome on the frontier, and there's a role for government intervention. Analogous result for consumption externalities. There's nothing special about having this on the producer side, so I won't go through this in detail. But basically, if consuming the good has an externality, then the demand curve is not going to reflect social marginal benefits. And same thing, you won't be at the optimal point, and you have deadweight loss. Okay, so what can you do about this problem? We've established that there's potentially a role for government intervention. What should we do about it? We're going to talk about 4 potential solutions: the Coasian bargaining solution, Pigouvian corrective taxation, regulation, and then basically a more sophisticated version of regulation, which is cap and trade. All right, the Coasian solution comes back to this point that I was stressing. that externalities emerge because property rights are not well defined. So suppose, for instance, that we're thinking about this market for cars where cars create pollution, and suppose we establish property rights to create markets for pollution. So what I mean, to be very concrete, is the following. So let's say we take the example of pollution in a river. Like every time I make a car, I dump some toxic chemicals in a river, and that has costs. Now, suppose there's a consumer who owns that river, like maybe there's a fisherman or something who's using the river to generate profits himself. Then what's going to happen in competitive equilibrium is you are going to end up bargaining, and firms are going to end up paying a marginal cost of D for every unit of pollution they emit, because the guy who owns the river is going to say, every time you make another car, I am losing D dollars because I lose fish or whatever, or I lose utility. And so since I own the river, you don't have the right to pollute it. You have to pay me some amount in order to compensate me. And the equilibrium is going to be that you're going to end up paying the guy D in equilibrium. So how is this equilibrium going to emerge? Imagine that there are a lot of rivers and there are a lot of auto plants. So it's a competitive model, right? So I can locate my plant in any number of places. Then people are going to say, if you pay me D dollars, then I'm willing to let you come locate the plant near my river. That's going to be the market clearing condition. And so as a result, the marginal cost of production is now going to be C prime of X plus D, because the firm owner is going to recognize every extra car that I produce. I have to pay this guy the D dollar charge, the fee, and that's going to bring us back to the first best, right? So even without the government doing anything, if the government simply says, I now give property rights of the river to the consumer, you take care of the problem completely. You don't actually need the government to do anything. That's COSA's main idea. What I think is furthermore quite interesting and intuitive once you think about it is it doesn't make sense whom you assign the property rights to. So there's nothing special about having the consumer own the river. If you have the firm own the river, you get exactly the same outcome. And why is that? You just got to think about opportunity costs, right? So the firm could say to the consumer, look, I'm going to make this many cars, but if you pay me D dollars, then I will cut back on the number of cars. And the consumer is going to say, okay, that is worth it to me. I want to pay D dollars because I bear this cost for every extra car that's produced. And you end up getting back to exactly the same point where you were before. Okay, so why don't we just do this and not worry about externalities in the government? I think there are two major limitations of the Coasian solution. The first is transaction costs in bargaining. So when you think about how externalities actually work, the important externalities, they're not sort of one-on-one externalities, where if you think about like the loud music kind of example, you might actually imagine that we don't actually need the government to come in and do some complicated thing. People will work that out themselves by literally bargaining, right? That's the Coasian solution. But if you think about the more important externalities like pollution, there are too many people involved who are bearing the costs and potentially getting the benefits from emitting that pollution. And so really, you need millions of agents to coordinate and bargain. The way I like to think about it is basically you need to reduce transaction costs in some way, right? To make this feasible, you sort of need an association to represent all the consumers. So what is the government? It's basically that association, right? The government's basically saying to firms, in principle, acting on behalf of consumers, saying you have to pay X to emit this amount of pollution. So in a sense, it motivates the kind of thing we're going to talk about. The other thing is that you're relying very heavily on the fact that the market for pollution, if you take the Coasian approach, this market for pollution with the river and so forth has to work properly. And we know that there are other reasons markets might break down, like asymmetric information in particular. And that's potentially a concern here because it's often not crystal clear who exactly is responsible for the pollution, what exactly is the damage. And that's the type of environment where markets are not going to function very well, right? Because you have the types of reasons we've talked about where the market can unravel when you have asymmetric information, but also just more generally, you can see that you'd get a lot of inefficiency or litigation if you're constantly disputing who actually emitted the pollution, how much you actually got hurt, and so forth. Okay, so I think the Coasian solution is not what you can rely upon for large-scale problems like global warming and so forth. So that motivates thinking about direct government methods. So that leads us to the next thing, which is the familiar idea of corrective taxes, going back to Pigou. So how would you think about fixing this problem? You impose a tax equal to the marginal damage. What I call MD here, this is basically like what I had as little d in the basic model. The marginal damage from producing another unit of the good. And that's going to restore Pareto efficiency and maximize social welfare. So let's just see how this works in this graph. So we were in this market equilibrium here, and then I impose this tax of t. I'm basically going to shift the marginal cost curve upward. And if I get the t right, I can bring us back to this point. So obviously one of the challenges is that you need to know, in order to set t properly, you need to know what those marginal damages are. And that's difficult to measure in practice, as we'll talk about when we come to the empirical work. So that's the price-based method, very simple idea. And then another simple idea is regulation. So if you come back to this graph here, this kind of looks indirect, right? It's like saying, I know I want to get to Q star, so I find the price, the tax that's going to get me to Q star. But if you know you want to get to Q star, why don't you just tell people that you can only produce Q star? Like, why don't you just regulate that you can only emit this much pollution or whatever, right? Rather than trying to infer the right price to get them to the level of pollution that you want anyway. That's the idea of, maybe a much more direct method is just regulation, right? Quantity-based restriction. I am going to require that you reduce pollution to a fixed level, or you face some sort of legal sanction. Another way you can think about regulation is basically a nonlinear tax. So rather than having a fixed tax for each amount of pollution that you reduce, we say if you're in violation of this law, in essence, we put an infinite tax on you. Like, that's illegal, right? You get fined. And below that, there's no tax. It's another way to think about it. So same outcome as the Pigouvian tax in the basic model. You're going to move people to the desired level x2. But there are two important disadvantages which are not incorporated in the super simple model that we started with here, one of which comes to the question you just asked about production efficiency, and the other is about allocative inefficiency. So these problems arise because when you price pollution, you're giving each firm marginal incentives to do better, basically. Whereas when you just set a cap, there are no marginal incentives for the firm. So let's take a couple of concrete examples of what that does. So first, suppose you have heterogeneity in costs of pollution reduction across firms. So for some firms that are, let's say, making cars, it's maybe very complicated to find a different technology to reduce pollution. But maybe, in a different industry like hotels or something, they can get people to use less towels, and it's much less. It's cheaper for them to reduce pollution. So because it's only the total level of pollution that matters, what's socially optimal is for the hotels to reduce pollution more than the car industry, right? But if you just cap industry by industry, say this is the maximum amount of pollution you can emit, or firm by firm, you just have a regulation on the amount of pollution, you're going to get an allocation inefficiency in that the wrong guys are going to be doing the cutting. That would not happen with the price method in principle, because each person would cut however much is desirable given his marginal costs. So if your marginal costs of cutting pollution are very high, you wouldn't bother doing it. But for a person for whom it's very cheap, they would try to save money by doing that. So the price method looks better from that perspective. And so then that also relates to the production technology choice, which I think is particularly important in a dynamic model. So think about if you can innovate and find more green technologies, if the only constraint the government imposes is that there's some fixed standard below which you have to be, like auto fuel emissions or something, then unless you update those standards over time, which is actually what the US does to some extent, you have no incentives on the margin to find better technologies. But if it's a price system, you do have incentives to innovate because you have to pay the government for every unit of pollution you emit. And so you want to constantly find better technologies. You profit from that. So that's why you would never do regulation, I think, just in a very bare bones way of just imposing a quantity for each firm. What you would actually want to do, and what people talk about a lot, is a cap and trade system where you have a market cap and then you allow trading. So how does that work? So the way this would be set up is through an auction, right? So the government caps the total amount of pollution that's allowed and then auctions the permits to firms. So they say, we are going to auction off 1 million permits for units of whatever pollutant you can emit, and whoever wants can buy them. And there's going to be some market clearing price that emerges, especially if you allow trading ex post, right? So the idea is you have this auction, or another way you can do it is just give each firm a certain number of permits. It doesn't matter. Like give every firm 10 permits. But then the key thing is after you give the permits, you allow them to trade ex post. So the fact that you've only issued a fixed number of permits ensures that you get to the level of pollution reduction that you want. But then you don't care who's doing the pollution reduction, so you just let that happen efficiently and let the market determine who ends up doing it in equilibrium. So it's kind of, the way I think about it is like this is a hybrid of regulation and the Coasian solution. The idea is essentially that you create the market. You say, I want a certain amount of CO2 emission. I've decided like that's acceptable. And then I'm going to let the market sort it out because I've now created this market with the permits. So that's, I think, like a very elegant way to think about it. And how does it solve the two problems that I mentioned? As I've been saying, in equilibrium, the firms with the highest marginal cost of reducing pollution are going to end up buying the permits, right? So the car guys are basically going to buy the permits from the hotel guys in the example I was giving. And if you set the total number of permits to achieve the social optimum, you're going to get both allocative and productive efficiency with this system. If you then think about a dynamic version of the model, you still have incentives to innovate because you don't have to buy these permits if you develop a cleaner technology. So now what I want to talk about is how do you choose between the tax, the price method, and the quantity command and control method once you've fixed it up in this way to deal with the allocative efficiency and dynamic inefficiency problems by allowing ex post trading, all right? So this is the Weitzman paper. So the price mechanism, as we've just talked about, is identical to the quantity mechanism in the simple model once we allow for the tradable permits. So how do you choose? Do you want to use taxes or do you want to set quantities? So in this very nice paper, Marty Weitzman shows that the key factor that determines whether you want to use prices or quantities is the shape of the marginal benefit and the marginal cost curves. And in particular, when you have uncertainty about what these costs and benefits are, which is very realistic. We don't actually have, the government doesn't know what's the marginal cost of reducing pollution for each plant and so forth. So when you have uncertainty, then the price and quantity methods are no longer equivalent. And then you can see there's a nice principle in terms of which you choose depending upon the shape of the marginal benefit and marginal cost curves. And that has become, I think, the standard way of thinking about where you want to do regulation and where you want to do price-based methods. So let's talk about the Weitzman model in a simple way related to our framework. So I find it easiest to think about the Weitzman framework if we write the model in terms of units of pollution reduction starting from the market equilibrium. Okay, so there's a certain private market equilibrium in terms of, X million cars are going to be produced per year. And that generates a certain amount of pollution. Let's now call Q the amount of pollution reduction you do relative to the million units of pollution or whatever you were emitting in the market equilibrium. So in the market equilibrium, Q equals 0. But the idea is because of these externality costs, I want some positive Q. And why do I want some positive Q? Because there's a social benefit to pollution reduction, which I'm going to call B of Q. But there's also a cost to reducing pollution, which is that either automakers have to produce fewer cars, as in the simple model I was talking about, or in the more complicated model where they can choose technologies, they have to invest money in developing more efficient technologies. Either way, there's some cost of reducing pollution. We're going to call that C of Q. So as I was saying in the simple model above, if you just want to map it back to that, the marginal benefit of pollution reduction was this constant D. And so that was a model where B of Q was D times Q, or B prime of Q equals D. And the marginal cost, because the only way you could change pollution was by making less cars, is given by the loss in surplus from producing one less car. What do we lose when we need to cut pollution by 1 unit? We lose U prime of X minus C prime of X. Okay, the difference at that level of production, the amount of surplus generated. More generally, as I was saying, the marginal cost can be interpreted as the cost of reducing pollution through the cheapest possible method. Think about a firm optimizing. The way in which they're going to reduce pollution is going to be either by making less cars or by finding a better technology, whatever the cheapest way is, right? And so that's going to generate this outer envelope C of Q function, which is what we're going to think about here, right? Okay, so here's a graphical representation of that. Let's take the case where the social marginal benefit of reducing pollution is just some fixed number, just in this graph. And then the marginal cost of reducing pollution is given by this increasing function here. So there's like a convex cost of reducing pollution. I have to find more and more difficult technologies. And so what happens in the market equilibrium? Well, the private marginal cost equals the social marginal cost in the unregulated equilibrium. And so I bear a cost to reducing, I bear a cost to reducing pollution, right? No matter what, whatever the government does. But even though the social marginal benefit is a positive amount, the private marginal benefit to the firm is 0, right? Like I don't care about the amount of pollution. I'm not going to do any pollution reduction. And so the market equilibrium is that we have Q equals 0. Because there's no incentive to do anything. And what we would like is to get to Q star, all right? So that's the setup. I'm just saying that algebraically, as I was saying, in the equilibrium, we get Q equals 0. The social optimum, what we want to do, the way to write it in terms of pollution reduction is we want to max B of Q minus C of Q. First order condition is to set the two marginal values equal, and with no uncertainty. So let's start, think about the case without uncertainty first, as we were before. We can obtain the optimum either with a price method or a quantity method. It makes no difference. So the price method would say you have to, by law, do Q star units, and the quantity method would say I'm going to find the price, I'm going to set the price such that it equals C prime of Q star. And so then you are going to optimize and end up choosing Q star. And it makes no difference. I can achieve the same level of welfare with both. Okay, so now we get to what Weitzman's actually about. What happens if there's uncertainty? So suppose the cost of reducing pollution is C of Q comma theta, where theta is a state variable. It's a parameter that the government doesn't know. So one way to think about it, in a very simple case, is that you have a bounded support for the distribution of marginal costs. You know the marginal cost lies between some lower bound and some upper bound, and the mean value is going to be given by MC mean. Let's say the planner's objective is to maximize expected social welfare. So he's just going to integrate over theta and say which policy is going to generate the highest amount of welfare in expectation, given that I don't really know how much it costs GM to reduce pollution. So formally, mathematically, what I want to do is choose one of two options. Either I choose P or I choose Q directly. And these generate two different expected welfares. If I choose Q directly, I get this expected value, so B of Q minus C of Q theta, taking the expectation over theta. And if I choose P, then the firm is going to choose Q given the P that I set, and then I'm going to get the expected value given whatever the firm ends up choosing, integrating over the thetas. All right? So Weitzman's insight is that the choice between these two policies depends in particular on the steepness of the marginal benefit curve. And so let's see why that is graphically. So basically his point is which you want to choose depends upon B prime of Q. Right? So let's start with the case where the marginal benefit curve of reducing pollution is steep. So that's shown by this diagram here. So the marginal benefit curve being steep means that B prime of Q is falling very rapidly as you raise Q. All right? And let's start with the case of quantity regulation. So let's say I set the quantity so that we get to the optimum if I'm at my expected marginal cost. So MC mean is what I expect the marginal cost to be. The marginal cost could be as high as this upper bound, it could be as low as this lower bound, and it could be somewhere between, all right? But let's just say for simplicity that there are just two states of the world, or you know, the three states of the world. It could be this, it could be that, or it could be that. So if it happens to be the mean, then I've gotten it exactly right. There's no deadweight loss. I told him to do 10 units of pollution reduction, and that's what gets done in equilibrium, and that's what we should have had. The problem arises when I guessed wrong on the marginal cost. And you know, let's say the marginal cost was up here at the upper bound. Well, now if I required you to do 10 units of pollution reduction, that was too much because the marginal cost was up here and the marginal benefit was only down here given by the green line. And so this yellow triangle here shows how much welfare we lost because I told you to do more pollution reduction than you should have in the social optimum. And conversely, if the marginal cost was actually lower than I thought, then I told you to do too little, and we get this deadweight loss triangle here, all right? So those are the expected, if you just think about, you know, I take an average over all these states, you can see that on average I'm going to have some positive amount of inefficiency because I don't know what the right quantity is. And so the average size of those triangles tells you the average deadweight loss that you'd expect with a quantity policy. Yeah. So remember, this is all pollution reduction. So it's slope downward, meaning every extra unit of pollution reduction that you do, there's a diminishing marginal benefit to that, right? Or another way to think about it is, as I'm making more and more cars, there's a diminishing marginal value of producing every extra car, right? Because the people have declining marginal utility. And so when I reduce pollution, there's going to be a diminishing marginal benefit to reducing pollution. Does that make sense? I mean, it's just like the usual concavity condition. So there's a lot of, if we're living in a very polluted environment, then there's a lot of value to cutting back on pollution. That's basically what the intuition you're capturing. And if the level of pollution is not that high, then the marginal benefit is a further reduction is not that high. So you're just trying to capture the rate at which the benefits of pollution reduction fall. Well, no. So I think it's better to, the effect you're talking about, that the surplus, that there's more surplus generated from the production of an extra car when you have very few cars, that's embodied in the marginal cost curves in the way we're thinking about it here, all right? So you're right, that if you think about the fixed D model, I should have been clear about this. In the fixed D model, the marginal benefit would just be a flat line. That's what I had here, right? Okay. But I am thinking about a model now, to be clear, where the D itself is changing with the quantity. You're right. So that's important. That's why the marginal benefit curve is downward sloping here. Okay. So in particular, the marginal damage of pollution has got to be increasing in the amount of pollution. So as a result, the marginal benefit of reducing pollution is concave. Okay? So, so the next case, okay, so this is quantity regulation, and we see that it has some expected costs. So we compare that now with price regulation. So how does price regulation work? I say, okay, I think the marginal cost curve is going to be given by this blue line. And I set the price at the appropriate level in order to achieve the optimal quantity given that marginal cost curve. So how do I figure out that price? Well, I know that the firm is going to choose to reduce pollution up to the point where the marginal cost equals the price, right? So if I pick this price, then I am going to get the quantity that I want to achieve, all right? Now, what happens if the marginal cost curve is higher or lower than I expected? Well, the firm is still going to reduce pollution, find a better technology, up to the point where the marginal cost equals the price. And so if it ends up being that the marginal cost curve is up here, then it's going to end up picking Q2. And if the marginal cost ends up being down here, then it ends up picking Q1. Yeah.
Is this all under cap and trade? You have to choose either the price or the quantity? I'm wondering.
It's all, to make it as simple, it's comparing prices with cap and trade. That's the general way to think about it, okay? But I think the simpler way to think about it is assume there's no heterogeneity across, like there's just one firm and there are no dynamics, okay? That's the simple version of the model. So then there's no difference between regulation and cap and trade.
Right, but if you choose cap and trade, you have to choose either the price or the quantity, is that right?
Oh, if you choose cap and trade, you would choose the quantity, right?
Okay.
What to cap at. You don't choose the price. That's the idea of cap and trade, yeah. But in this, none of those issues are arising because it's just one firm model, static. I can either pick quantity or I can pick price. That's it. All right, so if I pick price, the point I'm making is that you will end up with quantities of either Q2 or Q1, and both of those are going to generate inefficiency because if, again, remember the marginal cost ended up being up here, you should have done this much pollution reduction. You should have improved the plants up to this point. But you only end up improving them up to this point, and so you get that yellow inefficiency. And then conversely here, you've done too much and you get this deadweight loss triangle. Okay, so now let's just look at this visually side by side. And you can just see immediately that the average size of the inefficiency with the price method is higher than if you use the quantity method. Okay, and we'll now talk about the intuition. But the result here is if the marginal benefit curve is steep, as in this case, you want to use quantity regulation and not price regulation. So why is that? It's actually very intuitive. If one way to think about it is if you think about the optimal width of the optimal quantity choice, the band of optimal quantities, if you knew what the true cost curve is, when you have a steep marginal benefit curve, the band of potentially optimal quantities is very narrow. In contrast, the band of potentially optimal prices, look at what price you'd need to set to get to the optimum in each of these different cases, it's very wide. Okay? So the simple mathematical intuition is there's a lot more scope to make a mistake with the price choice than the quantity choice. Intuitively, what's going on? The steep marginal benefit curve, one concrete example of it is like some sort of toxin in the air where if you're below 10 units of this toxin, it makes no difference for your health. And if you're above that unit, it's going to kill you, okay? So take that extreme example. That's like a vertical marginal benefit curve. You do not want to miss on the quantity there, right? You want to make sure with zero probability you're over 10 units of the toxin because otherwise everybody's going to die. So you don't want to use a price method because with the price method there's some chance the firms will say, oh, it's not, marginal costs end up being high, I'm going to emit 12 units of the toxin. So you want to make sure you get the quantity right. And so that's why when the marginal benefit curve is steep, you want to tend to use the quantity method. Yep. Okay, so then the converse case, which you are seeing intuitively, is the flat case. We could do the whole thing again. And here you see the triangles look bigger for the quantity than the price, and it's exactly the reverse logic, right? The bandwidth of optimal prices is very narrow. So if we're back in the case, so as Vijay was asking, if we're back in the case with a flat D, then you know for sure you want to use the price method because you just want to set P equals D. There's no, you don't need to worry about uncertainty at all, actually. So it's clear the price method is better there. And so the bandwidth of prices collapses relative to the quantities. So in understanding this, I think it's useful to think about, we're talking about uncertainty on the marginal cost side. Yeah. Okay, so suppose now there's uncertainty about the marginal benefit of reducing pollution, but that the cost is known. So flip it around. We were talking about applications where we don't know how costly it is for GM to reduce pollution, but we do know the benefits of reducing pollution. In practice, it might actually be the reverse. It's a lot of debate about the benefits of reducing emissions, and maybe we have some sense of the costs. So what's interesting here is that the price and quantity policies are actually totally equivalent in this setting because the level of pollution is completely determined by the marginal cost curve. The marginal benefit curve is totally irrelevant. So if I impose a given quantity, then obviously I achieved that quantity of reduction. And if I know what the marginal cost curve is, then I can back out exactly the price that will produce that quantity irrespective of what the marginal benefits are. So in other words, what's going on is that the level of quantity reduction is determined, notice, purely by the intersection of the marginal cost curve with the price. So what matters completely is where the marginal cost curve intersects the price. It's totally irrelevant what the shape of the marginal benefit curve is. And that actually relates to why it's the absolute slope of the marginal benefit curve that matters and not the relative slope. And so the general point is that uncertainty matters only when it is about the cost or benefit schedule for the agent who's making the decision about the level of pollution reduction. So if in this market it wasn't the firms that were deciding the amount of pollution reduction, but whoever's benefiting from reducing pollution, then if you had uncertainty on the benefit side, the price that you set, the quantity that it generates would be determined by where the marginal benefit curve intersects the price. And so then uncertainty on that side of the market would end up mattering, right? So if the consumer chooses the level of pollution reduction, then uncertainty about that consumer's marginal benefits will end up mattering in equilibrium. Okay. All right, so is that clear or not clear?
I'm confused.
Confused by this slide or the one before?
No, this next one, this last point you're making.
So here it's clear why it's uncertainty about the marginal cost that matters, right? Because that's the side of the market that's choosing the quantity. So suppose now that the quantity was chosen by the guy on the benefit side of the market, all right? So the amount of pollution reduction that gets done, like the amount of trash we pick up or whatever, is determined by the people who are benefiting from the pollution, all right? Then the quantity that you're going to get to is going to be determined by the consumers, correct? Or like by whoever's doing the pollution reduction. So my point is, it's uncertainty about that person's benefits or costs, relative benefits and costs, that matters in terms of choosing between prices and quantities. It's uncertainty about the cost and benefit schedule of the decision maker that's critical. And that's what you see here in the basic Weitzman setup as well. Okay, so all of what we've talked about until now has been a model where the only problem is the externality. There's no other thing that the government is trying to do. But in practice, the government is also trying to generate revenue, trying to redistribute money, and do the various other things we've talked about in this class. And so you can't get back to the first best. And the type of models we've been talking about, aside from these issues of having uncertainty, if you knew what the size of the marginal damage from the externality is, you could literally fix that and get back to the first best. So there are many deviations from the first best that, in practice that we care about. Probably the most important one is that the government also needs to raise tax revenue to finance public goods or to redistribute income, if you're like in the Merleesian type setup. So the next paper we're going to talk about is the Sandmo analysis of optimal tax policy with externalities and a revenue requirement. So it's basically like Ramsey plus Pigou, right? So here, I'm going to set it up just slightly differently from what we had before so that it connects to the Ramsey model. So let's denote by d of xn. Now I'm going to allow this to be a convex function rather than a constant. The externality cost of consuming good n. And we're just going to assume for simplicity that only the nth good has an externality cost. Everything else is like the standard goods in the Ramsey model. Let's let W be the wage rate on labor income if we allow a labor decision. That's not important. And QI denote the post-tax price. PI is the pre-tax price. Tau I denotes the tax. Z denotes non-wage income as usual. Producer prices we assume are fixed as in the basic Ramsey model. All pre-tax prices, for simplicity, we're just going to normalize these PIs to 1. Okay? Individuals are going to have utility functions of this form where now we've added this d of xn term, which reflects the externality. And individuals maximize their private utility subject to the usual budget constraint. So the individual's maximization program is written by this Lagrangian here, which is utility, notice not including the externality term, that's the key thing, plus the budget constraint where lambda is the multiplier on the individual's budget constraint. You maximize that and you get an indirect utility function v of q, and then you can write the government's problem as max w of q, which is now no longer just v of q as it would be in the Ramsey model, but v of q minus d of q, subject to the revenue requirement, right? Tau I xi greater than or equal to r, so connect to the Pigouvian problem. Pigouvian problem has r equals 0. So you have no reason to raise taxes except to fix the externality. And then the solution is going to end up being that you just want tau n to be d prime of q. So let's just introduce a bit of notation which goes back to the Ramsey solution. Let's let theta be the marginal social welfare gain from levying a $1 lump sum tax. So remember, this was the thing we talked about before. If we relax the government's budget constraint and allow you to levy a $1 lump sum tax, what's the value of that? So by the way, why here am I not allowing lump sum taxation? So if I allowed lump sum taxation, what would the solution be? Lambda is the marginal value of relaxing the agent's budget constraint. Let's let tau IP denote the optimal Pigouvian tax rate, meaning solution to this problem when r equals 0. And so we know tau IP equals 0 for goods 1 to n minus 1, no externality on those. And tau IP equals d prime of xn for good n, the marginal damage from consuming good n. Let's let tau IR be the optimal tax rate. So that is the solution to that problem when d of xn equals 0. And let's let tau I denote the optimal tax rate in the actual model we're studying here, which has both of these features. Sandmo's tax rate. So the main result of Sandmo is that these problems are mathematically additive. So you can express the optimal tax rate as the Ramsey rate plus a Pigouvian correction. So to make this easy to see, let's consider the case where the Slutsky matrix is diagonal, so you have 0 cross-price elasticities. You'll remember from the Ramsey model that we went through a derivation which got us the inverse elasticity rule. So if you forget about the tau IP for a moment, we get tau I over 1 plus tau I equals this thing here. That was the formula we got from the Ramsey model. What Sandmo shows is what you end up wanting to do is tau I minus tau IP over 1 plus tau I equals that. That's what the optimum ends up being if you work out the algebra, very similar to the Ramsey model. And so then just do a little bit of rearranging. You rearrange this and you can show that tau I equals tau I p plus tau I r. That is tau I r, the Ramsey optimal tax rate. You can write the fully optimal tax rate as the sum of these two components. So what I want to be clear about is that this does not mean you solve the Ramsey problem and you get an optimal tax of 5%. You solve the Pigouvian problem, you get an optimal tax of 3%, and then you conclude the optimal tax is 8%. That's not how it works, because even though that's how it looks mathematically, it's like the usual sufficient statistic type of thing, where in this formula, all of the terms depend upon each other. This is not an explicit formula for the optimal tax rate. Okay, so it's a useful analytical representation, but it's not an explicit formula for the optimal tax rate. So what do I mean? When I raise the Ramsey tax, I'm going to obviously affect the equilibrium amount of consumption. And if I'm in this d prime of d of xn situation where every extra car we consume has an increasing marginal damage, then when I impose a higher Ramsey tax, people are going to consume fewer cars, and that's going to lower the optimal Pigouvian tax. And likewise, when I impose the Pigouvian tax, that's going to generate some revenue, which is going to change the multipliers, which is going to change the optimal Ramsey tax. So these are not two separate exogenous things. They both are functions of all the parameters of the model. Okay? And so really, this is just like a nice mathematical way to represent what's going on. You can't actually solve the two problems completely separately. I think the qualitative lesson that you get from Sandmo's analysis is that what you want to do is directly remove the externalities, basically fix the prices to get them right, to equate social marginal costs and social marginal benefits, and then raise revenue optimally. That's sort of the idea. And so what that means is, so you might have the intuition, like maybe it's good to tax cars because we know that in order to use a car, you have to consume fuel, which generates an externality. So what Sandmo tells you is, no, even if in the utility function, like notice we're putting no structure on this utility function, right? So fuel and cars are going to enter as complements in this utility function. It doesn't make a difference. You still want to have zero Pigouvian tax on cars, and you want to levy the Pigouvian tax completely on fuel. So the way people refer to that principle is you want to directly address the externality. You never indirectly address the externality. There's no point in doing that. You might as well directly tax fuels, and then you might tax cars for a Ramsey reason, but that's a separate.
And combining with the Ramsey model, you wouldn't actually fully subsidize it to get it to the right price because it's distortionary?
Yeah, so there's actually a debate on that currently in the literature on whether, so do you want to, when you think about subsidizing something, take the marginal cost of raising public funds into account or not? And if you think about it, the short answer is that if you think about it in the Ramsey world, the answer is exactly like your intuition, yes, because there's a deadweight cost to raising those funds. Turns out if you think about it in the Merlesian model, the answer is no, because you are optimizing the tax system, and so to first order, there's actually no cost. Another way to say that is in the Merlesian model, you're allowed to levy a lump sum tax, okay? There's nothing ruling that out by assumption. So you could raise the money by a lump sum tax, which is not going to have any efficiency cost. And you would have, if you were optimizing the tax system, equated the marginal cost of raising money with the lump sum tax, because that instrument is available, with whatever else you have. And so then the optimal policy is going to be one that compares the marginal benefit of the subsidy with just $1. You don't take the distortionary cost into account. So it sort of depends. Lewis Kaplow has been working on this recently. It depends upon whether you re-optimize the whole optimal income tax system when you're making that decision. Okay, so the questions you're asking are related to this double dividend debate, which is kind of like, do you get two things for one when you raise revenue by correcting these externalities. So here's a claim that you often hear in the media that people talk about. Like, why don't we tax gasoline more? That has a double benefit. We already think people are driving too much and there's too much pollution, so it's going to raise social welfare from that perspective. And we're going to collect money. We know we need revenue for the government. So in this type of setting, basically we can reduce other distortionary taxes, and that also improves efficiency. So this is great. We should be taxing these things more, right? So this logic is clearly correct if you're at a corner solution where the revenue requirement is below what is generated by the optimal Pigouvian taxes. So like coming back to the point Pascal was making with the lump sum taxes, if you can generate all the money the government needs through the Pigouvian tax, then of course you should just use the Pigouvian tax, and in the process of correcting the externalities, you'll satisfy your revenue requirement. Now in practice, that's totally unrealistic, right? We don't think that we're just going to finance the US government by correcting externalities. So the more realistic case is we're already, let's say, at a Ramsey tax interior optimum, okay? And now I wanted to talk about exactly the question I think you had asked, that suppose we discover now a new thing that generates a negative externality. Suppose somebody comes along and says the production of computers actually generates negative externalities. Is there a double dividend? Is there twice as large a benefit from taxing computers once we've made this discovery? And the answer is no, if you started at the Ramsey optimal tax system. So the idea is you did not have this information. You solved for optimal taxes across all the end goods. Now you're going to raise taxes on computers from a Pigouvian perspective to correct that externality. But you don't get a further first order benefit from reducing taxes on all the other goods because you already set the taxes optimally so that there was no first order benefit from raising the taxes on computers by epsilon and reducing the tax on something else. Okay? So you relax, so you do get a benefit to the extent that you are correcting this externality with the Pigouvian tax, because that is a first order cost that you are now eliminating from the system. But because you were at the socially optimal set of tax rates from a revenue raising perspective, you don't get to count it again. That's the idea, okay? You only really get the single dividend of improving the environment because you were starting from the optimum from a revenue generation point of view.
So if you're not at a Ramsey optimum,
then you do get a first order benefit.
right, but then is that an argument for having a Pigouvian tax rather than this cap and trade system? Because you get this other benefit from
But cap and trade, no, but cap and trade can generate revenue for the government, generates a tremendous amount of revenue for the government because you auction off the permits.
After you've done the initial auctioning, you don't get any more revenue.
So then you're in a dynamic model where you've like levied the tax once and you're not levying it period by period, and then there are issues of, is that, right, that becomes an issue of timing. I mean, that is a great, yeah. No, I mean, this is theory, right? We're not in the empirical part of yeah. I'm just saying conceptually, this argument that you get a double dividend from Pigouvian taxes, whether it's correct or not depends upon whether you think you've set the tax system optimally. Another way to think about it is, if you really think you're going to get a gain from the Ramsey point of view, then you didn't need to discover that this thing had an externality to fix that. You should have just done that anyway, right? So, so the general theme, I think, of this literature is that you want to think about the externality problem separately, and you want to think about the optimal tax Ramsey sort of problem separately, at least conceptually, all right? So you don't need to worry about other aspects of the tax system when you're thinking about measuring externalities. All right, so we'll stop here and we'll talk about empirical work in the next class.